Good morning to everyone. I am Esteban Rodriguez, PhD student from Politecnico de Torino, and I am also part of the Rescue ETN project, which faces reliability challenges in modern embedded systems. Rescue ETN is supported with fundings from the European Commission. Today, I will share with you the results of a proposed modular in-field strategy for the Divergence stack in general-purpose graphics processing units. The main goal of this work is to explore modular approaches to design functional test solutions using software-based self-test methods in GPUs. The outline is composed of an introduction and background of the topic, a general description of the architecture of GPUs, the proposed testing approach, some experimental results, and finally some conclusions. Currently, the general-purpose graphics processing units are effective solutions in high-demand, data-intensive applications, such as image and video processing, and most probably, the current device you are using to see this presentation is using one of these devices. Moreover, the high capabilities of these technologies has been applied to more complex applications, such as the safety-critical ones in the automotive and industrial robots industry, where the real-time constraints, high-performance computation, and human interactions are common. In this field, the reliability of functional safety are main concerns, so the GPUs employed to perform computer vision and machine learning operations, such as the samples presented here, should include structures, methods, or solutions to avoid the interference or faults arising during the field operation. These faults can compromise the execution of the application and the stability of the system, so potential solutions should be proposed in order to avoid the potential issues of faults. The rising of permanent faults during the operation of a GPU can be caused by multiple factors, such as aging or wear out. Moreover, in some cases, the application can continue the operation generating a wrong result, which then causes an error in the application, such as presented in the example. These errors can be critical, considering that embedded GPUs, which are those employed in automotive and robotics, may propagate the error to the application and compromise the operation of the entire system. In this work, we explore modular approaches to develop functional test programs as a method to answer the observed question. The in-field test of digital devices can be performed in several manners, but it's possible to divide them into main strategies. The first one is the design for testability structures, which are included during the design phase of a design as a dedicated structures to provide the test stimuli and also to provide the detection capabilities to a target module. Some examples include the BIST and MBIST structures. On the other hand, there are some software-based self-test methods, which are based on the design of special programs that provide the required test stimuli and also are able to detect faults affecting or arising a target module. This method is a non-invasive approach to perform functional testing and can be developed to fix requirements for an application. For the purpose of this work, we explore the SBST approaches to develop test programs in the GPU architecture. The architecture of a GPU is mainly based on several cores, which are commonly known as SIMT cores or SMs, depending on the terminology employed. These modules represent a main operative unit in the GPU, and inside them, the execution follows a single instruction, multiple data paradigm. So there are several execution units allowing the parallel operation of the same instruction. A local controller assigns the task to each core, and depending on the type of instructions to be executed and the conflict among operands, a total number of threads will be executed in parallel, or a total number of threads will be stopped in every single clock cycle. Inside the SM, the control flow mechanism to operate a parallel task is managed by an internal scheduler and dispatchers. These modules mainly control the operation of the parallel threads when divergency conditions are present. Some information must be stored by these controllers, such as the information of the active threads, the starting points and finishing points address, and some may include additional information regarding the addresses of several resources in the GPU core. More in detail, the divergency is present when one or more threads in the same group take different paths produced by conditional operations in the code, such as the yellow and blue paths presented here in the example. In this case, some threads operate the yellow path. Meanwhile, the other must wait until the path is finished and the resources are now available to start the missing path. In the end, the convergence is reached when all threads of the same group execute the same instructions again. As observed in the figure, the location of the divergency and convergency points and the active threads on each moment must be known in order to perform the operations on each path. It means that this information must be stored, and actually is stored in a memory or stack, saving the information for divergency management. This procedure is commonly applied independently of the architectural details of a GPU core. For our purpose of developing SBST solutions, we employ the FlexGripPlus GPU model, which is an open source course developed by Politecnico di Torino on top of the GPU model developed by the University of Massachusetts. The model is based on the G80 architecture of NVIDIA and also is compatible with the CUDA environment. On the right, you can observe, remarked in the red, the divergency stack memory used or present in the GPU model. Currently, the general-purpose graphics processing units are effective solutions in high-demand, data-intensive applications, such as image and video processing, and most probably, the current device you are using to see this presentation is using one of these devices. Moreover, the high capabilities of these technologies has been applied to more complex applications, such as the safety-critical ones in the automotive and industrial robots industry, where the real-time constraints, high-performance computation. Considering the structure of the stack, the method also uses the operational features to propose a set of generic assembly routines in charge of performing the injection of a test pattern and the propagation and the detection of the fault. For this purpose, the divergency and convergency generation and the activation of the specific threads are used to define a set of functions to generate the test patterns. Finally, we consider the structure of the stack and the effect of applying a convergency and divergency for managing the access to the memory. We also include some checkpoint routines in order to allow the test division in parts, and also the use of signatures for fault detection and fault propagation to a local memory. With these functions, we were able to develop two modular approaches for the stack. The first is called nesting, and in fact, it takes advantage of the nesting of some routines in order to generate the test patterns and also to propagate the effect of a fault from the stack to an external memory. The method starts generating a divergency where the taken and not taken subroutines can be executed in a serial manner. Inside each block, the signatures are updated. In the taken path, an additional divergency can be inserted to change the line entry as presented in the scheme. The same two paths are applied, and again the taken path, a new divergency routine can be added to change and move to the next block inside the stack memory. In the end, this process can be repeated up to the limit of the memory. The convergency point is reached after a checkpoint procedure that decrements the pointed line entry. However, As the target test patterns depends on the address and the total number of active threads, the previous procedure must be repeated several times, following patterns as presented in the schemes in blue. It means that a large number of repetitions is required to effectively test the whole stack. The positive of this strategy is that it's possible to directly describe in the CUDA level or the CUDA programming. The second strategy is called sync trick and searches a more controlled manner to access each entry line. In this case, the proposed method starts with one or several sync operations, which affect the pointer in the stack, so accessing a different line entry. Then a divergence is generated and the two paths are operated. Both paths are used to update the signature. The convergence is reached and a checkpoint is used to determine if the operation is correct or some faults collapse the operation of the entire program. This procedure can be repeated independently or sequentially or only in specific line entries as presented in the schemes in blue. The main advantage of this method is that the description of the test can be divided in several parts. In contrast, this test program strategy cannot be mapped into a high-level programming environment such as CUDA by the lack of translations used for the synchronization routine to managing the stack memory. As experimental results, we configured the GPU model with one core, and then we performed several fault injection campaigns at the RTL level targeting permanent faults using the Stukat fault model. We also employed 4 representative benchmarks for comparison purposes. Finally, we also employed some variations of the test programs, such as the addition of some PC functions, which basically include all the test patterns for the PC field in the stacks. As can be observed in the table, the general features for the two modular strategies are evaluated for 1, 2, and all line entries when possible. As observed, the number of instructions for the nesting strategy increases up to more than 900,000 for the entire stack and more than 12,000 for the sync trick version. In terms of execution time, also the sync trick requires less time to test one line entry and the entire stack. In terms of fault coverage, some applications were also used to observe the normal coverage obtained by them and in order to compare with the proposed programs. As observed, the stack memory requires the development of special test programs considering that the obtained fault coverage in the application is not enough. In the sync trick and nesting test programs, the percentage of fault coverage is moderate when applied without considering the PC functions. However, the fault coverage reaches up to 97 and 98% when combined, which means that these two modular test techniques are effective for the target module. It's worth noting that the individual approaches were also used to test the entire memory in the case of the sync trick approach. Finally, as observed, other of the features of the sync trick method is the low percentage of crashes or hangs detected in comparison with the nesting approach. As conclusions, we introduced and evaluate two modular functional test strategies, sync trick and nesting, based on the SBST approach showing a good percentage of fault coverage. The modular and scalable approaches employed in the development of the test programs allows the selection and evaluation of different options for the functional test. The modularity and the scalability of the sync trick solutions also allows the reduction in latency when executing the test, which means that can be used also for in-field operation. As future plans, we plan to extend the technique to evaluate the controller in the module and also to explore other modular mechanisms in the development of functional test programs. Thank you for your attention, and if you have questions, please write us to the contact email.